Hello everyone. So let's start with today's class. So this is session number 2 in which we are discussing the questions related to the subject of heat transfer that will help you to solve the assignments which you have to submit it in the ongoing week. So in the last class we had covered the content of week 1 so that you would be able to solve the questions related to week 1. So in the previous class we had covered this introduction basically motivation of the course, introduction to conduction, so that you would be able to solve this weekly assignment 1. So I think this is to be submitted by tomorrow. So today we will be discussing the content of week 2 so that you can solve this weekly assignment number 2. So we will just revise what all we studied in the last class, in the last class, that is week 1, and then we can move on to the basic theory necessary to solve the questions of week 2. Okay, meanwhile if you have any doubt you can just unmute yourself and ask, or else write in the chat box also. So we studied this course objective in particular for this course. So what was the motive behind this course? So the main objective is to quantify the heat process in various systems. So how will we do that? These were the following steps. So what basically heat transfer was, we defined it by using the concept of this transfer and this driving force. So this transfer involves movement of certain quantities due to interaction of system with the surrounding. So whenever any kind of transfer is occurring, there is a driving force responsible for that. So if the driving force due to which this transfer of any quantity is occurring is due to the temperature difference, then we call it as heat transfer. Similarly, if the driving force is chemical potential, then we call it as mass transfer. So in heat transfer, we will be concerned with the transfer processes or the exchange that occurs due to the temperature difference between system and surrounding, or two systems that we can say. So we discussed the applications in terms of this IT products such as CPU, liquid cooled gaming PC, in mobiles. Then we discussed this application of this human skin. Then the main chemical engineering heat transfer applications, whereby we can see multiple modes of heat transfer such as condensation, such as conduction, convection, radiation, and then this phase change operations such as condensation, boiling. All those can be seen in this chemical engineering applications. Then we briefly covered the three main modes of heat transfer, that is conduction, convection, radiation. We studied the basic laws such as this Fourier's law for heat conduction, then Newton's law of cooling, and then we moved on to this composite. Then we moved on to this resistance concepts, which can help you to solve the questions easily, whereby you have multiple modes of heat transfer such as conduction, convection. It would also be useful that when you have this different kind of materials that are in connection with each other, so basically composite materials, so you transform each of these diagrams into these resistance diagrams, and then whatever the heat transfer rate is you express is at temperature difference upon the resistance. And then we introduce this concept of overall heat transfer coefficient, whereby we have this conduction, convection. So how can we represent the entire heat transfer coefficient using a single value? So for that we introduce this concept of overall heat transfer coefficient. So yes, that was all from week 1. So in week 1 we were mainly focused on the system, which were, I think, which were in Cartesian plane. So they were either rectangular block or cuboid or similar kind of stuff. So we were just only working with the systems that were a rectangular block. So in today's class we will be discussing that what will happen if we are having any other geometry such as radial geometries such as cylinder or sphere. So in case of this rectangular block, if I had to just show conduction over here, so this is the cross. So if my heat transfer is occurring through this direction, so this is my x. So this is the direction of my heat transfer and also the direction of my x. So over here qx will be input and qx will be output. So for this system we can write the heat flux or the heat transfer rate as Ka dt upon dx. So here you can see that A is the cross-sectional area through which the heat conduction will take place. So this is the cross-sectional area of the rectangular block. So this A does not depend on the length or the x direction. That is, A is not a function of x. That is why we can describe the resistance of this system straight away as qx upon, so we can write this as dx upon Ka, and this was our resistance only because this A was not depending on this direction x. But in case of any other geometry such as cylinder or radial system, this area will be a function of radius r. So for example, if we take a cylinder and to just draw the side view of this cylinder, so this is my no, you can say that in case of this cylinder also. So here, see, this will be my heat conduction area. So the heat conduction area, let's consider if this is my Q. So if heat is being generated through a wire passing within the cylinder, then the heat conduction area will be this. You can write it as 2 pi RL. So this area is a function of R. So similar case would be encountered in case of cross section of the sphere also, or any other geometry whereby the heat transfer area varies with the direction in which the heat transfer occurs. So in such a scenario, we can't straight away write this resistance as delta x upon the K times of the area. What we need to do is we need to consider an incremental element of, in this case, let's just consider an element of area of this width dr, and then we have to just integrate it across this entire length dr. Integrate the area across the entire length. So these fundamentals, keeping this fundamental in mind, we will move on to our next class. So in today's class, that is week 2, we will cover this resistance in radial system, then heat generation in plane and cylindrical wall, then we will heat generation with introduction to extended surface. So here in this last 3 section, that is extended general formulation, extended surfaces, fixed cross section, we will discuss about the importance of fins, and we will define what do we mean by fin. So yes, I hope this much is clear. Let's move on to this the first section, that is resistance in radial system. So as discussed in the earlier, whereby we had discussed this cylinder and sphere, and there the area was dependent on radius. So for this case, let's just consider this as a kind of conical shape which has been cut from the top, whereby the radius yes, so here the heat transfer area, or if the conduction is occurring in this direction as shown in the figure, the cross-sectional area will vary with x. Okay, that is A will be a function of x. So in such case, as I mentioned earlier, the effective resistance will be the integral of the entire length dx upon the area, and area should be a function of x. So upon K. So this will be my resistance. If it was a pure rectangular block, then we remember it as delta X upon K A. But in case of such a system, we have to take this integral. So yes, you can encounter such systems in case of this tapered cylinder also. Tapered cylinder also. So using the same concept, you can find the resistance of the cylinder as well as sphere. So the area of the cylinder through which the conduction will occur if the heat generation is this, then we call it as 2 pi RL. Okay, so the area is 2 pi RL, and if you just put the area over here 2 pi RL and then integrate it, then you will get the resistance of the cylinder as this term, conductive resistance. Similarly for sphere, it will be this term. So these two formulas you need to remember. That is, for cylinder, the resistance will be ln of R2 upon R1 upon 2 pi Lk, where R2 is the radius of the outer cylinder and the R1 is the inner radius of the cylinder. Similarly for sphere, the resistance is 1 upon 4 pi K into product of radius R1 inverse minus R2 inverse. For other geometry, you need to derive, they are not that straightforward. Also, there is another concept of this logarithmic area, that is ALM is equal to A1 minus A2 upon ln of A1 A2. So you can use this concept also to reach to the same equation. So this formula we straight away derived using this Fourier's law. An alternative way to solve these problems, considering multiple, considering this radial profile, considering what this general equations in terms of this, you can say the heat balance, we can derive the same formulas as shown over here. So it's the general equations we derived in the last week that denotes the heat transfer is given by this equation. So for example, I have a heat generation term Q dot, which is occurring in a block whereby this is my y direction, x direction and z direction. So the heat generation within this block, where the heat transfer will occur in all three directions, can be written using this term, that is del. So using this term, and if we expand this derivative, you will get this term. Now if the heat conduction is occurring only one direction, in x direction, then we can straight away write this term. Similarly, we can write this equation in terms of, we can write this derivative, second derivative, in terms of this radial coordinate also. So in terms of radial coordinates, the expansion of that derivative will become this term. And in most of the cases in this course, you will be only considering a single direction in terms of this radial coordinates. So you can just neglect all of this term and then expand this term. You can just put this term, that is 1 upon r del r del t upon del r plus q dot is equal to rho Cp dt by dt. Now the earlier cases whereby you are studying were all this steady state, that is whatever heat is going inside, the same heat will go outside, that is there was no accumulation term. So if you want to derive this same formula, that is for the steady state case, this term will become 0. Similarly, depending on this heat generation term, you can neglect it, or else you can just integrate this equation and you will be getting, you will overall reach to this equation in terms of this temperature profile. And then you can straight away use this formula use this formula and get, so basically you will, in terms of this radial profile, it will become q is equal to minus of k 2 pi rl dt by dr. So this dt by dr term, you can get it from differentiating this equation, and if you differentiate it, and you will be ultimately getting this qr, that is the heat flux through the radial system. But you don't need to remember this term. You can just straight away remember the resistance of the cylinder, and then just use this delta T upon R to find this heat flux, the heat transfer through this cylinder. So if we just expand this, so given this equation, and I have this rectangular block, whereby at one surface my temperature is T1, another surface temperature is T2, and some heat generation is occurring through the center of this block by this q dot. Then for the same system, we can write the temperature profile in terms of x as this equation. So this equation you can derive by putting appropriate boundary conditions in this equation. That is, at x equal to, let's say, minus L, the temperature will be T1. At x equal to plus L, the temperature will be T2, and then you can solve those equations using those boundary conditions to arrive at these equations. Now if, let's say, if the temperature T1 is equal to T2, and it is basically equal to the, let's say, assume surface temperature Ts, then you can put these equations over here, so this term will get cancelled out, and this will ultimately become Ts. That is, Tx for a block with uniform surface temperature will become q dot upon L square upon 2k 1 minus x square upon L square plus Ts. Okay, so now if you want to find the temperature at, so here you can see that the temperature is a function of x. An alternative way to remember this equation or represent this equation is to, we don't need to remember this entire temperature profile, every time. What we can do is we can just find the temperature at the center of this slab, and then use the formula that we will be deriving, that is the correlation between the relation between the temperature at the center of the block and this surface, in order to find the temperature difference between the center of the block and at any x. So for that, if you can just put the value of x equal to 0 in this equation, and then you will be getting the temperature at the center of this block. So using this, you can find this q dot, that is at center q dot. So overall you can get this original equations that can be used to find the temperature at any given x without using this entire equation. So basically, if you put this equation number 3 in equation number 1, so equation 1 was this term, so q dot, you need to put it as this 2k upon L square, then T minus Ts, so you will be getting these equations. So this is an useful equation, that is Tx minus temperature at surface upon temperature at center minus temperature of surface is equal to 1 minus x square upon L square. So this equation, but remember that this equation is only valid when you are having a block whereby uniform heat generation is occurring from the center, and the temperature of both the surfaces are same. So these assumptions you need to remember. Similarly, you can write the same thing for the radial system. That is, if you are having a cylinder and heat generation is occurring at R equal to 0, then you can straight away write this temperature at any radial distance R minus temperature at surface is equal to temperature at center minus temperature at surface to 1 minus r upon r naught square. So both of these equations are more or less similar in nature. So these are the ways in which you can find the temperature distribution or temperature profile for the system, which are governed where the area increases with the distance or the direction in which we are moving. So until now we calculated the ways to just calculate the heat transfer rate or the heat transfer flux for any given geometry. So now we will be moving on to this concept of fins, whereby we discussed that in order to, for a given geometry such as this, for a given cubic void, if I want to increase the heat transfer from the surface, so what all physical modifications do I need to make into this cuboid or into this rectangular block, whatever we are having. So in order to increase the heat transfer, so heat transfer is governed by this equation H A Ts minus T infinity. The heat transfer coefficient is not something that you can manipulate. So heat transfer coefficient is given by this K upon delta. So this comes from the boundary layer theory. So you can't change the thermal conductivity or the boundary layer. You can't change the thermal conductivity of there. So you can't manipulate basically this H for any given systems, but you can always change the kind of fluid that you are dealing with. So the other term in this equation is this area, that is H A delta T. So A is the surface area through which the heat transfer occurs. So what you can do is you can increase the heat transfer area in order to increase the heat transfer rate. So if you want to increase the heat transfer rate, you can increase the heat transfer area. So one of the methods to do this is by incorporating fins. So what we do is we just extend this surface by using additional material. As shown in the figure over here, I will just use these extended portions, and these extended portions which are used to increase the heat transfer surface are called as fins. So using this heat transfer fins, we will increase the heat transfer area, which will ultimately increase the heat transfer rate through any given systems. So one of the major applications you can find this is in terms of cooling. So this diagram is basically of your CPU, whereby you can see that in order to cool your processing unit, you have such kind of fins. So they basically increase the heat transfer area so that your CPU cools faster. So in order to derive the necessary equations that will help us to find the temperature at any given length of the fins or the heat transfer through the fins, we consider this heat balance across this elemental section or this small section. That is, if I am considering this section, so this is the direction x, so I can write it as qx, and if the thickness of this small section is dx, so it will become qx plus dx. Then we can just write the heat balance across this system, that is qx minus of qx plus dx plus whatever heat transfer is occurring through this small section, plus h into small area, we are calling it as delta as. T is the temperature of this at the surface, and T infinity is the ambient temperature. So you can write this qx at qx plus del q by del x, and ultimately you can again expand this term in terms of this radius as shown, in terms of this temperature gradient as shown over here, then take limit delta x tends to 0, and ultimately if you just solve these equations, put all those values of the area over here, area that for conduction it is a cross section area, similarly for convection it will be the surface area. If you put the value of area and then integrate it over the entire length, that is x equal to 0 to L, you can get these equations, the general equations for this fin. So whereby you can just define this theta as T minus T infinity, that is a temperature difference between the surface and the ambient air temperature. And then you can define this parameter M as under root of HP upon KAC. So P is the perimeter of the surface. So for example, if we are having this rectangular fin, the perimeter will be twice of this width upon twice of this thickness, that is 2 of T by W, and this area, cross-sectional area, will be WT. Similarly, in case of cylinder, the perimeter will become pi d and the area will become this pi d squared by 4 as shown over here. So this thing you need to remember, this P and AC. Here usually students make mistake while calculating the cross-sectional area. They consider the surface area. So this thing you need to remember, that the area over here is the cross-sectional area. So you can then solve these equations. So this is a second order differential equation. So the roots of this equation, that is d square minus m square, will be plus or minus m. So the temperature difference will become C1 e raised to minus of mx plus C2 e raised to plus mx. So this is the equations, and so theta is nothing but the temperature difference as shown over here. Then depending on the boundary conditions, that is whether convection is occurring at the tip of the fin, or whether no heat exchange, that is adiabatic nature, is present at the tip of the fin, or if the tip of the fin is maintained at the fixed temperature. So considering all those boundary conditions, you can derive this different theta for each of these cases as shown in this table. For example, if we are having convective flux at the end, that is at this surface there is air present, and due to which this inside this there is conduction and outside this there is convection. So if convection is occurring at the tip of the fin, then we can write the temperature difference given by this equation. Similarly, the heat transfer rate will be given by this equation. And over here, this M is nothing but under root of HP, K, AC, and theta B. Theta B is the difference, that is TB minus T infinity. TB is the temperature at the base of the fin. Over here, temperature at the base of the fin. Similarly, for adiabatic case, you can write this equation for prescribed temperature, that is, if the temperature difference is fixed, you can just write this equation. And for an infinitely long fin, you can straight away write these equations. So all these equations will be useful to solve the numericals related to the fin. Then we define, so how can we evaluate the performance of the fin, that is whatever fin that we are using is effective or not. So for that we have just two performance metrics. One is the fin effectiveness and the other is the fin efficiency. So the fin effectiveness, we define it as the ratio of the actual heat transfer with fin upon the heat transfer that would have occurred if no fin was present. So in this case the fin is present, so considering this entire system, the heat transfer rate will be QF. But if this fin was not present, that is, we only had this surface, so for that the heat transfer rate will be nothing but HA delta T. So the temperature of the surface is Ts and temperature of the ambient air is T infinity, so it will become Ts minus T infinity. So the fin effectiveness is defined as the ratio of QF upon HA Ts minus T infinity. So this QF, you can get it from this table. Now in case of infinite fin, you can remember this formula, that is Kp upon HAC. Then we have another metric to judge the performance of the fin, that is fin efficiency. So that is again defined as the QF, that is the actual heat transfer through the fin, and the maximum possible heat transfer through the fin. So the maximum possible heat transfer through the fin would occur when the entire fin is at this base temperature. So if the base temperature is TB, so if this entire fin is present at the temperature of TB, then we can say that the maximum possible heat transfer is occurring. So yes, for the formula for that will become ultimately this QF upon H AF upon theta B, where AF is nothing but the the overall surface area of the fin through which the heat transfer or the convective heat transfer will take place. So yes, two main thing to remember is the fin effectiveness is defined as the actual heat transfer upon heat transfer without fin, whereas this fin efficiency is defined as the actual heat transfer upon heat transfer that would have occurred if the entire fin was at the base temperature. So over here there are this formula for fin efficiencies. So this was the summary for today's class. That is the theory that we discussed until now. So if you have any doubt, you can just write it in chat box or ask, and then we will move on to solving the questions related to the class. So the key takeaway from the entire theory that we discussed from the today's class related to the extended surfaces: fins provide an additional surface to dissipate the heat through convection. Though 3D simplified 1D analysis provide design insight on effectiveness and efficiency. So yes, over here I have just shown the derivation of those terms. So that was all the theory necessary to discuss the questions related to today's class. So now we will move on to the questions. So I will just show you the questions and you can try solving it. I will give you around 5-10 minutes and then we can discuss the solutions to those questions. If you have any doubt related to today's class or earlier classes or any of this assignment question that you want to solve, you can just discuss, or else we will start with question solving. Okay. So let's start with the first question for the day. So the question is: an uninsulated thin walled pipe of 100 mm diameter is used to transport water to equipment that operates outdoors and uses water as a coolant. So that is, we have been given that we are having an uninsulated pipe. So this pipe has a diameter of 100 mm. So if we just draw the cross sectional area over here, so phi is equal to 100 mm, and this is used to transport water to the equipment that operates outdoors and uses water as a coolant. So yes, basically nothing but water is flowing through this tube. Then we have been given, during particularly harsh winter conditions, the pipe wall achieves a temperature of -15 degrees Celsius and a cylindrical layer of ice forms on the inner surface of the wall. That is, the temperature at the surface in winter, the temperature of the surface reaches -15 degrees Celsius, and since water is flowing inside, a layer of ice forms inside. So a layer of ice will be formed inside. So if we just show it over here, so this is the layer of the ice. Then we have been given if the mean temperature of water is 3 degrees Celsius and convective coefficient of 2000 watt per meter square is maintained by the inner surface of ice, which is at 0 degrees Celsius, what is the thickness of the ice layer? So here we have been given that the mean temperature of water is 3 degrees Celsius. That is, over inside the temperature is 3 degrees Celsius. Then the ice will be at 0 degrees Celsius. And again the outside temperature we have been given it as minus 15 degrees Celsius. So you can just write it as Ts is minus 15 degrees Celsius, and then you will be having some resistance due to ice. Then we have this temperature of the ice as 0 degrees Celsius, and then you will be having some convective resistance due to the water, and temperature of water is 3 degrees Celsius. And for this given system you have been asked to find the heat transfer, I think you have been asked to find the thickness of the ice layer. That is basically this thickness, let's just call it as T. So that thickness you have to find, and the given parameters are the convective coefficients 2000 watt per meter square, then the thermal conductivity of ice, and then you have been just given the hint to mathematically solve the resulting nonlinear equations. So here you can see that two heat transfer processes are taking place. So the one within the ice is conduction, and then we have this convections, and we have this all the temperatures of the surfaces. So what you can do is that you can just write a simple energy balance across this system, and you will be getting this Q convection is equal to Q conduction, and then you can write formula for both of these terms, that is delta T upon R convection is equal to delta T upon R conduction. So this R convection will be nothing but HA delta T, and R conduction will be in terms of the formulas that we derived. So you can use that, put the desired values and try to find the radius. So I will give you around 5 minutes. You can try solving that, and then I will just solve the question in front of you. So you have to find the thickness of ice. So the conductive resistance for the cylinder is, I will write it as ln of R2 upon R1 upon 2 pi k. So you have to use this formula over here, and you will get the solution. So try solving it. So right now it is around 7:42. I will discuss the solution at, let's say, 7:50. So you can try solving within 80 minutes. So I hope you were able to solve. So let me just share the solution with you. So yes, as discussed, you had to equate both of this conduction and convection via energy balance, that is Q conduction is equal to Q convection. So Q conduction, you can just write it as delta T conduction upon R conduction is equal to delta T convection upon R convection. So temperature difference for this conduction as shown in this resistance diagram over here, so is minus 15 minus of 0, whereas temperature difference for convection is 0 minus 3. Okay, so minus 15 minus 0 and 0 minus 3 upon, so we write this R conduction. So R conduction for this radial system of the cylinder, we wrote it as ln of R2 upon R1 upon 2 pi KL. And for convection, it is nothing but the overall surface area. So it will become 2 pi R1H. Okay, so R1 upon H. So R1 is the distance between the center, that is at R equal to 0 and R whereby we find the ice, whereas R2 is the entire radius of the cylinder, that is I think given as 100 mm by 2, so R2 is 50 mm. Okay, so just keep that in mind. R2 is 50 mm and R1 is nothing but R2 minus thickness of ice. This we need to find. So you can just put the values over here. So you will be getting 15 by 3, that is 5, into 2 is 10 pi H R1 is equal to 2 pi KL upon ln of R2 upon R1. So just divide this equation by R2 so that we can get this ratio R2 upon R1, so that will be easier to solve. R2 over here also will be having R2. So over here we can just put the value of R2 as 50 mm. So that is, we will be getting this term, taking it over here, ln of R2 upon R1 upon this term, this will go over here, R2 by R1 is equal to K upon HI R2 into this temperature difference wala term. So K is over here, 10 K and 10 R inversely proportional, so it will become K by 10. So you can put the values over here and you will be getting ln of R2 upon R1 upon R2 by R1 is equal to 0.097. So let's just treat it as x. So that is, we will be getting ln of x is equal to 0.097 x. That is nothing but, so x will become exponential of 0.097 x. So you have to solve this equation. So you can start by taking the value of x equal to 1. So for that you will be getting the new x 2 as e raised to 0.097 into 1. So if you solve this, e raised to 0.097, you will be getting it as 1.101. 1.101 is our x2. So basically the ratio we will only use the first iteration. If you keep on increasing the iteration, this value will eventually converge to some fixed value. So that will be our ultimate x2. So x2 was nothing but R2 upon R1. We found the value is 1.101. R2 we already know is 50. R1 we have to find. So R1 will be 50 upon 1.101. So it will come around 45. So the thickness of the ice will be 50 minus 45 is equal to 5 mm. So that was the question that was asked. The thickness of the ice for the given system will be 5 mm. Yes, so the same is shown over the solution steps. So this is the second question. You can again try solving it. So the question number 2 states that a uniform internal heat generation Q dot equal to 5 into 10 raised to 7 watt per meter cube is occurring in a cylindrical nuclear fuel rod of 50 mm diameter under the steady state conditions. The temperature distribution of the form, we have been given this temperature distribution, whereby we have been given again this parameter. So the fuel properties are also given, and the main question that we have been asked is what is the rate of heat transfer per unit length of the rod at R equal to 0 and R equal to 25 mm. So that you have to find. So we have been given a cylindrical rod, and uniform heat generation is occurring inside the cylindrical rod. So Q that is being produced inside this rod, and the temperature with respect to this R is given as temperature profile is given as this quadratic term A plus B R square, then A, the value of A and B we have been given, and then we have been asked to find Q upon L. So again you will be using this concept of the heat transfer for these radial systems, that is Q is equal to K, A is a function of R del T upon del R. So this you can use to find the value that has been asked, that is Q by L. The temperature gradient you can find by differentiating this equation. So you can try solving it. We'll discuss the solution soon. Hello. So yes, let's solve this question number 2. So the heat flux, the heat rate for this radial system, as we mentioned, was Ka R del T upon del R. The area is 2 pi RL del T by del R. So this term we have to find. So using this equation, that is T as a function of R is A plus B R square. That is del T upon del R will become twice of BR. So this value you can just put over here, and you will be getting Q is equal to K into 2 pi RL into twice of BR. That is nothing but Q is equal to 2 pi K R square this will be 4 pi K R square B into L. In the question, we have been asked to find the heat transfer rate per unit length. That is, we have to find Q by L, this entire term as 4 pi K R square B. This we have to find for R equal to 0 and R equal to 25 mm. So you can straight away put the formulas over here and get, if you put R equal to 0, you can see that this entire term will become 0. That is, at R equal to 0, Q by L will be 0. At R is equal to 25 mm, you can just put value 4 into pi into K is 30, 25 is 2.05 square, and the value of B is 4.167 into 10 raised to 5. So yes, you can try solving this and get the value of Q at R equal to 25 mm as 0.98 into 10 raised to 5. This from the given options, this 0.98. So this option B is the correct one. That is, option B is the correct one. Now let's quickly move on to the third question. So the third question states that a one-dimensional plane. So meanwhile, if you have any doubt in the previous two questions, you can just write in chat box while I discuss this question number 3. So the question is, a one-dimensional plane wall of thickness 2L experiences uniform thermal energy generation of Q dot and is convectively cooled at x equal to plus or minus 50 mm by an ambient fluid characterized by T infinity is equal to 20 degrees Celsius. That is, we have been given a block so the thickness of this wall is 2L is equal to 100 mm. So energy is being generated uniformly inside this block with Q dot equal to 1000 watt per meter cube, and it is cooled at x equal to plus or minus 50 mm. That is, at the surfaces it is being cooled. Plus 50 mm minus 50 mm. So this will be x equal to 0 by the fluid of temperature 20 degrees Celsius. Then we have been given if the steady state temperature distribution within the wall, that is a steady state temperature distribution, is given as T of x is equal to A L square minus x square plus B. So then we have been asked to find the thermal conductivity of the wall as well as the convective heat transfer coefficient, that is K and H. So since the energy is being generated within this block and we have been given the surface temperatures and the temperature profile is also a function of X, you can write the heat balance equations in 3 dimension and then just equate the rest to term to 0 and you will be getting this term delta 2 upon delta x2 plus the heat generation q dot k plus alpha del T by del T. Since we have been given steady state over here, yes, the steady state temperature distribution, so we can just ignore this term and we'll be getting this equation. So similar to the previous question, you have to use this temperature profile over here and then on the basis of this so yes, you have to use this temperature profile over here, so you will be getting this term q dot and from that you will be getting the value of k, and then you can just use this energy balance across the surface, that is the heat conduction is equal to heat convection, in order to find the convective heat transfer coefficient. So right now it is 20:15. We will discuss the solution in 20:25 after 10 minutes. So this is the solution approach. You just have to put the values, then find the value of k from over here, basically differentiate this, put the value over here and find the value of k, and then write the heat balance in order to find the heat transfer coefficient. Since we were discussing this question number 3, so I was discussing this question number 3. So now we will just solve it. So as discussed in this slide, you had to write this three-dimensionless heat equation and then equate the term corresponding to y direction and z direction as 0. So that will give you the heat generation equation in along x as this term del 2t upon del x2 plus q dot upon k is equal to 0. And in the question you have been asked to find the value of k and then the heat transfer coefficient h. So first you need to find this term del 2 by del x2. So you need to differentiate this equation twice. So del 2 by del x will become a into 0 minus of 2x plus 0. The second differentiation would give you this term minus of 2 of a. So 2 of a. So this value you need to put over here and then replace the value of q dot in order to find the value of k. That is minus of 2a is equal to minus of q dot by k. That is, I am using this equation in this equation. I am putting those both. I am solving both of these equations simultaneously. So q will become k will become q upon 2a. So q we have been given as 1000 watt per meter cube. A we have been given as 10. So this will become 50. So the thermal conductivity of the wall is 50. So now in order to find the heat transfer coefficient, we saw that for the given block at the surface, at any given surface, we can just write the heat conduction is equal to heat convection. That is Q conduction is equal to Q convection. So it will become Q A del T by del X is equal to Q is equal to H. No. It will become K A del T by del X is equal to H A delta T. This AA get cancelled out. This del T by del X we found out from this equation as 2AX. 2AX into K, but we have to find the value at the surface. That is when X is equal to length. That is at X equal to L and the length is 50 mm. And H we have to find the temperature difference between the surface and the ambient air is given as temperature at surface minus temperature of ambient air. So now what we need to do is we will just straight away put the values. So H will be twice of wait a minute, this should be small a, twice of a, basically this term a. So it is 2a, putting x equal to L, value of k upon Ts minus T infinity. So can just put all those values, so it will come 2 into value of a is I think 10, length is 50 mm, value of k we found out as 50, then temperature at length L. So temperature we need to find over here. So temperature of surface will become, you can just put x equal to L, so this term will get cancelled out. it will basically be B. Temperature at surface will be B, that is 30 degrees Celsius, and the ambient temperature we have been given as 20 degrees Celsius. So 30 minus 20. So this will come around. So this will become 10. So this cancels out. 5, 5, 25, 5, 25 to 5. So this will come around 5 watt per meter square Kelvin. So that is option A. So in this question, we use this use this heat balance equation, and then the temperature profile was given. So in order to find the thermal conductivity, we just differentiated this term in order to get the second order derivative del 2T upon del x2, and we just straight away put it into this equation in order to find this K. And then in order to find the convective heat transfer coefficient, we just equated the heat balance at the surface. So now let us see another questions. So this question looks big, but it is a straightforward application of this fin-based approach, whereby you need to use the formulas mentioned in the table. So the question is, one method that is used to grow nanowires, that is nanotubes with solid cores, is to initially deposit a small droplet of liquid catalyst onto a flat surface. So as shown in the figure, I will also show it over here. So let us consider this is our surface. So we initially deposit a small droplet of catalyst, liquid catalyst. The surface and the catalyst are heated and simultaneously exposed to a higher temperature, low pressure gas that contains a mixture of chemical species from which the nanowire is to be formed. So this is exposed to a low pressure gas that contains the mixture of gases, which will be ultimately deposited in order to find the rod. Okay, the catalytic liquid slowly absorbs the species from the gas through its top surface and converts this solid material that is deposited onto the underlying liquid solid surface, resulting in the construction of nanowire. So yes, the reaction will occur, and ultimately these particles will get deposited on this catalyst in order to form such a kind of nanorod, a nanowire. So this was at some fixed temperature Ts, will be having some ambient temperature T infinity, and this material get deposited in order to find the nanowire. And the liquid catalyst remains suspended at the tip of the nanowire. So over here there will be this liquid catalyst. And then we have again considered the growth of a 15 nanometer diameter silicon carbide nanowire onto silicon carbide surface. Okay, so the diameter of this is given as 15 nanometer. The surface is maintained at temperature of 2400 Kelvin. So this surface is maintained at 2400 Kelvin. Then the particular liquid catalyst that is used must be maintained in the range of this range. So the liquid catalyst temperature should not go beyond 2400 Kelvin. That is why we keep the temperature of the surface as 2400 Kelvin. And it should be always below 30,000 Kelvin. That is the temperature of this fin, should be below 3000 Kelvin, so that the liquid catalyst is also below 3000 Kelvin. Then we have been asked that determine the maximum length of nanowire, that is basically this length L, that may be grown for the conditions characterized by H is equal to 10 raised to 5 watt per meter square and T infinity is equal to 8000 Kelvin. So T infinity is given as 8000 Kelvin. Assume the properties of the nanowire are same as for bulk silicon carbide, that is K is equal to 30 watt per meter Kelvin. So yes, we have been given some assumptions that will help us to solve the questions. So nanowire stops growing when the temperature at x equal to L is 3000 Kelvin. So over here you can just write that the temperature at the surface at x equal to L, temperature at the tip, not the surface, at x equal to L is 3000 Kelvin. Then yes, these are some general assumptions. So yes, we had been asked to find the maximum length. So you can consider this system as a cylindrical fin, and for cylindrical fin, we had this equation over here, cos h upon this. Since we haven't been given any specific boundary conditions except the maximum temperature limit, we can use this convective boundary conditions, that is at the tip there will be convection occurring. So you can use these equations, and we have been given these temperature differences. So using those temperature differences, that is nothing but theta upon theta b is given by these equations. So you use those equations in order to find the maximum length. So again, I think this will be a non-linear equation and you need to use a trial and error. So I'll just write these equations so that you can try solving it. So this is the question that we are solving. And the formula we have been given as, let me just put it up over here. So the formula, that is the ratio of the temperature difference, that is theta upon theta b, we have been given as cos hyperbolic m L minus x plus h upon mk sine m into L minus x upon the term that will be devoid of x, that is cos hyperbolic ml plus h by mk sine hyperbolic ml. So over here m is nothing but under root of hp upon ka. P is the perimeter, a is the cross-sectional area, theta is nothing but T minus T infinity, theta b is the temperature of the surface, that is Ts minus T infinity. So you need to put all those values in order to find the value of L. So try solving this question. This is a straightforward question, but you need to use a trial and error approach in order to find the length of the reactor. Since there is nothing more to solve, I will just straight away share the solution. So over here we are given T. So the temperature of the fin we had been given as somewhere over here. Yes, this 3000 Kelvin we can take. Kelvin minus the ambient temperature is I think 8000 Kelvin over here. Temperature of the surface is given as 2400 Kelvin minus again T infinity is this term. So this will be equal to this entire term. So you can just find the value of this under root of hp upon ka. The perimeter of the cylinder will be 2 pi r K, and the cross-sectional area will be pi r square. Pi will get cancelled on r. So we have been given in terms of the diameter. So in terms of diameter, we can just write this as h 4h upon kd. So you can put the related values, that is 4 into heat transfer coefficient, convective heat transfer coefficient h is given as 10 raised to 5. Thermal conductivity is given as 30. The diameter is 15 nanometer. So yes, you can try solving this and you will get the value of m as 9.43 into 10 raised to 5. So using this value, you will put it in this above equation and equate it to this term. So this term will come around 0.893. So that is, you need to solve this equation. That is 0.893 is equal to cos of m we found out as this 9.43 into 10 raised to 5 into length minus x. So you can, I think, put the value of x at x equal to L, since we had taken this 3000 Kelvin. So this term, the numerator, that is cos m, will become 0. Similarly, this term will also become, either of this term, this term will become 1 and this term will become 0 by putting x equal to L. So it will become 1 upon this simple term cos h ml plus h upon mk sin h into ml. Now you can put all this value of h, k. The only unknown remaining is L. So either you can use this iterative Newton-Raphson method, that is, assume a value of L and then keep on iterating until it converges, or else you can straight away put the value of L from the given option and then just check which of the following option match. So if you do that, that is, just put the value of all those 4 values and see whereby which of the value is more accurate. So if you put that the value of the length, that is the maximum length that you can grow, the length of the nanowire that you can grow will be around 510 nanometer. So let's discuss the last questions for today's class. So I will give you some time to read the question and then you can try solving it on your own. So this question is related to the fin effectiveness. So you have been asked to find the fin effectiveness for this pin fin. Just try solving it. Meanwhile, if you have any doubt, you can just ask to me. So let's try solving this question. So the fin effectiveness, we define it as the heat transfer rate through the fin, and the heat transfer rate through the fin that would have occurred if the entire fin was at the base temperature. And for that, we just write it as H, heat transfer coefficient, the cross-sectional area, and temperature of the fin upon temperature of the base. So this is nothing but this is theta b. So for this pin fin, the heat transfer QF is given as under root of H P K ACB 10 into theta b 10 H MLC, where LC is L plus D by 4. So this you can put over here. So this theta b and this entire term will get cancelled out. So you will be getting under root of H P K AC into 10 H MLC upon H AC. So now you can just put all the formulas over here in order to find the fin effectiveness. So yes, the perimeter, so pin fin is nothing but a small cylindrical fin, so the perimeter will be 2 pi r. So this term I am just calculating this ratio, 2 pi r into H into K, cross sectional area is pi r square upon H into pi r square. So this term will become 2 pi r cube into H into K. You can just take this inside the brackets, which will become H square pi square into r square. I hope I'm doing this correct. So now you can just cancel each of those terms. So ultimately, if you try solving this, so you will be getting 2 upon under root of H D by K 10 MLC. So the value of M is under root of HP by KA. So that you can calculate, and it will come around H into 2 pi r upon K into pi r square. So this will get cancelled out, this. So it is nothing but under root of 4H upon KD. So this will come around 37.1. So this value you have to put over here. LC is this term, and ultimately you can get this effectiveness. So I have to just prove that this ratio should be equal to this ratio, that is under root of H P K A C upon H A C. You can try solving this, but ultimately the answer, the effectiveness, you can just put all those values in this equation and it should come around 23.5. This should be the fin effectiveness. Okay. So this will become under root of HPKAC upon under root of HAC whole square. So this H will get cancelled out, this AC will get cancelled out, and in the denominator we will be having under root of HAC, and in the numerator we will be having PK. So that is under root of H under root of PK upon H into AC. Now you can just put the value of perimeter as 2 pi r. The cross-sectional area is pi r square, and then you can get these equations. So write it in terms of this diameter, so this extra 2 will be getting, so under root of 4 will become 2, and then you can just write this equation. So yes, that was all we discussed in today's class. So the main takeaway from today's class was we studied these systems whereby the cross-sectional area will depend on the radius or length. So in order to find the resistances, you have to consider a small element and then integrate it along the entire length. Then other thing we studied was, in order to increase the heat exchange rate through any given system, you can use these extended surfaces, also called as fins. So then we saw the derivation of the heat transfer through the fins in brief, and that will give us some equations. So we can straight away use those equations in order to find the temperature profile across the fin as well as the heat transfer rate. And then we studied the two concepts of heat effectiveness and heat efficiency. So yes, if you have any doubt, you can just write it in chat box or unmute yourself, or else we can end today's session. So since there are no doubts, we can end today's session. Thank you everyone for joining.